Hi, this is Mrs. Westmoreland, and today we're going to talk about converting chemical energy into electrical energy in a galvanic cell. So our task is to construct a galvanic cell for the reaction between zinc and nickel. We're going to place metal electrodes in 1 molarity solutions of the same metal ions. We'll want to calculate the standard cell voltage when that reaction occurs. We also want to write what's known as the line notation to represent the cell. And we want to draw a diagram of the galvanic cell, labeling anode, cathode, direction of electron flow, and direction of migration of anions and cations in the salt bridge. Then we also want to describe the changes you would see in each half cell. So before I begin, I know I'm going to want the metal ions with the metal electrodes, and I need to know those half reactions that will occur. So I use a table of standard reduction potentials to find those half reactions. Now all of these are written in the reduction direction, and so I can see as I scroll down, I have the nickel half reaction of nickel 2 plus 2 electrons becoming solid nickel, and it has a voltage on the standard reduction potential of negative 0.25 volts. And then I have the zinc one down here of zinc 2 plus 2 electrons going to zinc metal with a value of negative 0.76 volts. So one thing I know about a galvanic cell is that the overall potential will be positive. And so the more negative one will be oxidized, while the more positive one is going to stay in the reduction direction. So in this case, the nickel is going to stay in the reduction direction, while the zinc is going to be oxidized. So when I change those, and it looks like I've got 0.23 volts here instead of the 0.25 that was on the table that I just showed you, when I reverse the zinc half reaction to be oxidation instead of reduction, the value of negative 0.76 changes to positive 0.76, and I can add those two half equations back together to get the overall spontaneous chemical reaction with a value, in this case, of 0.53 volts. A little bit different if we had used the 0.25. So in our diagram of the cell, oxidation occurs at the anode. So the zinc metal in the zinc solution is the anode, and it is being oxidized, losing electrons. And the nickel is being reduced, so the nickel 2 plus ion solution with the nickel solid electrode is the cathode. And that is the part that is gaining electrons, where the reduction occurs. So we separate the half reactions, the oxidation half and the reduction half, into two separate containers connected by wires, which can be hooked up to a voltmeter, and also connected by a salt bridge, which helps to complete the circuit. So in the line notation, the metal of the electrode is written first of the anode, then the ion that is in the solution of the anode. Those are separated by a single line barrier. Oops, excuse me. And then the double line barrier shows the transition between the two different solutions. And then we have the ion of the cathode followed by the metal found at the cathode. And so you can think of the line notation as an ion sandwich. So the solutions are in the middle. The metal electrodes are on the outside. A single line represents a barrier between phase, so between solid and aqueous solution, and a double line represents a barrier between the two half reactions. So the zinc is oxidized at the anode, and the nickel is reduced at the cathode. And the electrons flow from the anode to the cathode. So as zinc loses electrons, the electrons flow in this direction, and then down the nickel, where they join up with the nickel 2 plus ion to plate out as nickel metal. In the salt bridge, which is there to complete the circuit, the Sulfur is usually filled with some sort of soluble salt, like potassium nitrate, which doesn't really interact with the chemical reaction, the net ionic equation. So because we have a buildup of positive charge at the anode, as the zinc ion solution increases, we need anions to balance out that positive charge. Otherwise, the electrons are not going to continue to want to leave as the positive charge builds up. And conversely, as the negative charge is reduced over here at the cathode because the nickel 2+ is being used up, now we have whatever negative ion was in the original nickel ion solution as an excess. And so we need cations from the salt bridge to flow towards the cathode to balance out that charge and allow the circuit to continue, because negative electrons are not going to want to migrate towards a buildup of negative charge at the cathode. So if we were to observe the changes occurring, then we would see that the zinc metal is withering away. Since zinc metal is the reactant, it's being used up. The concentration of zinc ions would increase at the anode. That would not have any visible change because zinc 2+ is a colorless solution. And then over at the cathode, the solid nickel would plate out, since nickel solid is a product of the reduction, and the nickel ion concentration decreases. In that case, since nickel 2+ is a green color, we would see that green color fading to colorless as this cell operates. Thanks for listening. See you in class.